Hi, welcome to the analysis, design, and simulation of a flyback, part 4. Okay, in this part, we're going to talk a little bit about the parasitics in a transformer. Correct that, transformer. Okay, and the main parasitic is leakage inductance. Okay, so we're going to talk a little bit about that, and then we're going to see how to model them in SPICE, how to use it, and how to use SPICE, or how to model the leakage inductance using both the coupled inductor model and the ideal model. Okay, so the first thing would be is what is leakage inductance? Okay, well, typically you want to create a magnetic field by putting a signal in here, okay, a sinusoidal, and that creates flux lines. And if you have an ideal transformer, you're going to get 100% coupling. In other words, that's what you want. You want 100, whatever magnetic flux are created in the primary, you want those to be coupled into your secondary, and you want 100%. So that would be the ideal. But because of the non-idealities, you never get close to 100%. You may get like 99.9 and not get the perfect coupling. So what does that do? Well, what it does is, if you have some lines that are not coupled, then what it does, it creates a little series inductor in series, and I typically donate it as LK or L leakage. So it's a little another series inductor in series with the transformer that's not coupled to these two windings. So it's a parasitic. So that's the leakage inductance that we consider as a parasitic. Okay. Now, how do you measure that? Okay, it's actually quite easy. What you do is you get your LCR meter and you do an open loop test. Open, secondary. Okay. Basically, you leave your secondary open, and then what you do is you measure the primary. And what you're actually measuring is you're measuring your primary and your leakage inductance. They're in series. However, the leakage inductance is very, very small. Typically, it's supposed to be small. So the main inductance that you're reading is actually your primary. Okay. So then what you do is, then you short your secondary right there, and typically you want this to be low resistance and low inductance. So you want a heavy gauge wire if you can get it, or maybe a braid, and short it as close as possible to the secondary windings. And what it does is, since you're putting a short, get a different color, basically you're putting a short across the secondary, which implies that you're putting a short across the primary. Okay, and if you do that, then since you're shorting across the primary, the main parameter that you'll be reading is the leakage inductance. So this, the short test, gives you an LK, which is your leakage inductance, and your open secondary gives you your inductance in the primary. Okay. So with those two measurements, you get that, and you get your leakage inductance, and then you use this formula, okay, and you get a K, which is a coupling coefficient, and that's the square root of 1 minus the leakage inductance divided by your primary inductance. Okay. Now, once you have those measurements, then you can use this K. Let's see right there. That K, whatever you calculated, you can use it in your spice. Now, in the example that I'm using a leakage inductance of 400 nanohenries with a primary of 120 microhenries. And when you put in the formula, I get 0.99833. Okay, so how to model it? Okay, if you're using the coupled inductor model, you know that you're going to have L1, L2, and then you also use the K. Okay, and when you define K, you're going to define L1, L2, and typically in my prior simulation I've been using a 1. Well, that's that K factor. So in this case, this, what you calculated, you defined it right there. Okay. Now, if you're going to use the ideal transformer model, then to add the leakage inductance is very straightforward. All you do is you get a separate inductor and you name it. You just put the value of the inductor, and of course you define your primary, and you're done. Okay, so how do we do it? Well, spice it and see how they work. Okay, right here, this is a coupled inductor, so it's L1, L2, and in the prior videos already mentioned how I use the curly brackets and the parameters and how to define them. Okay, and here's the K. Okay, K is the spice parameter, and here I put L1, L2, and then I define the coupling coefficient, which is 0.99833. Okay, so I have that, so it's already defined, and by doing that, Spice automatically puts or inserts a leakage inductance in series with L1. Now, if you're using the ideal transformer model, and here you can see that I just inserted L4, which is supposed to model the leakage inductance, and I'm using a 400 nanohenry, which is what I use to define this K factor. So just put it in series. Okay, so I'm going to go ahead and run both, and I'm going to be looking at the drain right here. I define the drain. I define it as coupled inductor. That way we can see. And then at this drain, I have it labeled as ideal transformer. And we'll go ahead and run it. That should be good enough. Okay, here I'm plotting the voltage output of both models. As you can see, it goes to 12 volts. And then on the bottom here is the drain. Okay, I'm going to go ahead and zoom in. Okay, and if you notice, okay, prior or subsequent simulations, when I did not have the leakage inductance, this was straight. Here now we have a ringing. Okay, now the ringing is caused by the leakage inductance. Okay, so let me go ahead and zoom out a little bit and get a little bit better zooming function. Okay, that's a little bit better. Let me see if I can get two of them. Okay, I guess I'll do one. Okay, now the ringing, let me go ahead and go back to the notepad. Okay, the ringing is because of the interaction of the leakage inductance and the parasitic of the MOSFET. Okay, it's basically your drain to source capacitance that that is ringing with these. So they're ringing at a specific frequency. Now that frequency can be determined by 1 divided by 2 pi Lk and the capacitance of the drain to source. Okay, so let's go ahead and let me see. Go ahead and okay. Go ahead and measure the frequency just to see if it's true, and I'll zoom in again just to be sure. Okay, so I'll put the cursor right there. And we get a frequency of 20.11. 20.11 megahertz. Okay, so if we go to MathCAD, let's see, it's 1 divided by 2 times pi. Times the square root. In this case, it was 400. 400. Okay. Times 10 to the negative 9. And the capacitance is, let's see, I use 150. 50 times 10, 12. Okay. And calculate it. So I get 20.54 megahertz. So it's a match. So that's pretty good. It says that we're pretty well convinced that the ringing or the frequency of this is because of the interaction of those. Okay, so what's the big deal of the ringing? Well, first of all, we can tell that when it rings out, let me go ahead and zoom out again. Okay, what it's doing, the leakage inductance, besides the ringing, is actually increasing the voltage that's across the drain. Okay, that to max. Okay, basically the highest is 90, 96, almost 96 volts. Okay, that's the peak, and the base of this is 47 volts. Okay, so basically you're adding quite a bit of voltage over this, and this ringing is also causing heat to be generated in your MOSFET. Okay, so those are two things. So, and the third is that you're creating EMI that could be conducted uh, back to the bus or radiated. So what do? Well, what you do is you try to damp it, and the way you damp it, go back here. Okay, since you have a circuit, you need to dissipate some of that power. So what you do is you add a capacitor. Okay, and you put a snubber resistor, and you add that right across your primary. Okay, now typically this value of the capacitor will be 2 to 10 times the value of your capacitance from drain to source. Okay, so in this case I'm going to go ahead and use let's use 450, which is 3 times. Okay, and then for the value of this resistor, that's supposed the value that I typically use is the square root of L of the leakage divided by CDS. Okay, so let's go ahead, see what kind of value we get. So we know that we have a 400. Let me increase this. I might not be able to see it. Divided by okay. So in this case we would use a 51 ohm resistor. So let's go ahead with the capacitor, and what I'll do is I'll add it to this model. The capacitor, make it 450 pico. Okay. Add a resistor, and we'll put it right across there. Just connect it, and then put 51. Okay, so now go ahead and rerun the simulation. Maybe I can shorten the time. So, basically what we're doing is we're snubbing it and we're taking some of the power dissipated into the MOSFET and dissipating it through the resistor. So we're putting a resistive load to dissipate that ringing, that energy. Okay, so now we zoom in. Okay, and you might not be able to tell, but let's see if I can the options be the ideal. Let's make that thin. Okay, and and couple inductor. Let's make it 2 times normal. That way we can. Should have been a little bit thicker. See if that works. Okay. Then, well, let me do this. The red is actually bleeding a little bit too much over. So, I'll put this, copy, paste it. That way you can see it better. Okay. So basically what I did is I copied the couple inductor, which is where I have the snubber, and I left this uh, the ideal transformer, which is unsnubbed, and you can tell that there's a big difference. Big difference. So, oh, there you can see it. See, you can see that you have the ringing, okay, the one that is unsnubbed. Now in the blue, it's snubbed. And you can see it more clearly here. And the other added is that now the voltage, instead of going all the way to 96, as it was going up here, okay, instead of going to 96, now the voltage at the drain only rises to 62, which is a big uh, savings in drain. In other words, you have more margin, safety margin. Okay, so this is the way you will model uh, the leakage inductance. And to deal with the leakage inductance, you add a capacitor and a resistor across the primary.